Finally, you decided to build a project. You get the data, you select an algorithm, you train on the data, but hey, you got a very bad performance from the model, a very bad performance. Your model did not perform well as you expected. What went wrong? What the thing did you did wrong? Take your life 2 minutes back. Okay, have a 2 minute flashback. What the thing? What was the thing that made your model perform bad or poorly? Got it? No? Let me help you. The two things, the two things that can go wrong, that can go wrong. Number one, number one is bad data, bad data, and number two is bad algorithm. Okay, these two define the whole system, whether it will perform good or not. Whether its performance will be on higher side, which will make some profit, or whether its performance will be on downside, whether it's making us devote more time. So we know that bad algorithm and bad data, that's the only possible cases that thing that can go wrong. Now we want a fix for it, because if we feed very bad data to a very excellent algorithm, still we'll get a very bad performance. Because if we don't get the pattern, how we'll predict? And if we have very the best data in the world, and if we have a very bad algorithm, it will not even work. Because even if you have a very good uh, a machine, if you do not have a very good input, it will never give you a very good output. Because garbage in, garbage out. If you input garbage, you'll get garbage. So what are the challenges that makes machine learning go in a wrong direction? So the two main things that I told about: bad algorithm and bad data. Okay, if we talk about the data, if our data, if the data can go wrong, what are the cases in which the data can be bad? Okay, what are the cases in which the data can go bad? So number one, if we are talking about data, yes. So for the data, the number one thing is that insufficient quantity of data. If we have insufficient quantity of data, then the model will never going to make it. Okay, the model will never going to make it, because we do not actually have the sufficient data to make our model perform well. Okay, so for example, if we pick a kid, okay, suppose there is a child, and we are and we want him to know about an apple. Okay, and we want him to know about what is a apple. So what we have to is that we have to go to him, and we have to repeat apple, 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 apple 100 times or few times, by showing him an apple. Okay, by showing him an apple and saying that it is an apple, and he or she will forever know about all sort of apples. Okay, he or she will know about all sort of apples with the shape and color. Okay, whether it's pure red, whether it's fed red, whether it's red but not red, is it round or what shape in it, or whether it is green or whatever, the toddler, the kid will know that what a apple it is. Okay, we just have to say and repeat it few times, and he or she will know what an apple is. But in machine learning, we are not there at, but in ML, we're not there at. For even a simple, okay, even a simple problem, we need a lot of examples to know what it is. Okay, what is the way it is. Okay, to work properly, we need like thousands of examples. We need thousands of examples to work properly. Okay, and if it is a complex problem, we need millions of examples. Are you getting that? So we're not there yet in machine learning where we just say it few times and it will know about Apple or anything. Okay, so the first thing that we know is that we need sufficient quantity of data. Okay, we need sufficient quantity of data for solving or for solving or having a pattern for a specific problem. Okay, and if we talk about data, then there was a research paper published in 2021. Okay, 2021. Okay, sorry, my bad. 2001. Okay, 2001, in which the Microsoft researchers, there were Microsoft researchers, you can go and search about them. Okay, Microsoft researchers named Michael, sorry, Mitchell Banco, Mitchell Banco, and Eric Bill. Sorry for my pronunciation. Eric Bill. So they represented and they told in the research paper that they for different ML algorithms. Okay, so what they did actually is that they got data. Okay, so let me create some space here. Thank you, Apple Notes. It will letting me to create some space. Very good thing. Okay, so what they did is that they got data. They got a lot of data and they fed it to different. Okay, and they fed it to. I need to have a eraser where it is. Why it is so small, man? Yeah. Oh, yeah. And they fed it to different algorithms. Okay? Different algorithms, different algorithms. And the result was insane because the data performed the data performed almost identical on the I'm sorry, the model performed almost identical. Okay, the model performed almost identical on the given enough data. So they got to the conclusion that having enough data means better performance. Having enough data means better performance. Okay, and the data matters more than the algorithm. For complex problem, it was more made popular, further made more popular by Peter Norvig. There was a person named Peter Norvig, which who told the world about that data matters more. Okay, the data matters more than the algorithm. In the paper called the unreasonable effectiveness of data. Okay, the paper, the unreasonable, unreasonable effectiveness, the unreasonable effectiveness of data. Okay, but what matters here is that how and from where we'll get the data, because getting data is not very cheap. Okay, getting data is not very cheap. Okay, and for example, if and for example, if I say two, what you will consider? If I say two or two, what you will consider? It totally depends on the context. It totally depends on the situation. So if you get confused when to use or on what scenario to use two or two, okay, if I just say by my mouth, even you get confused how a machine will know where to use two or two. It's totally depend on the context. So we have to feed it enough data to get to the pattern or to get to the conclusion where to use and where to not. Okay, yeah. So the first thing is insufficient quantity of data. So we need more data, better prediction, better pattern, and better you can say better performance. Simple as that. Now, second thing, the second challenge is that non-representative training data. Okay, so you got insufficient data, you solve the problem of insufficient data. Now you have non-representative training data, which means that if we are training for a model then we need all the scenarios. We need all the scenarios captured or should be in the data, should be in the data to make pattern, have pattern, or to have pattern, or to have some performance measure. Okay, so we need to have training set. Okay, so we need to have a training set which has all the representative of the data, all kind of data. Because if you're talking about, suppose I'm talking about your what I can say, like your town. Okay, so it does not only have one kind of people. Okay, it does not only have one kind of people. There are some people who do job. There are people who do businesses. There are people who do service. There are people like who would be doing nothing. Okay, so there are a lot of case scenarios which we need to have, which need to be present in the data to generalize. Okay, to generalize well. Okay, to generalize well, to know all the cases about the scenarios and situations, so that we can have a good generalization. Okay, so we need to have the every representative of the data. Okay, every scenarios to make it better. Okay, now moving ahead, we have yeah, poor quality of data. Even if we have sufficient data, if the data is poor, if the data is noisy, if it is has errors, if it has outliers. Okay, it is very poor, it does not have any quality, so then it cannot detect pattern. Because even after having sufficient data, if it does not provide the quality of the data, then it will never detect the pattern. If it cannot detect the pattern, it is less likely to perform well. Okay, very less likely to perform, oh man, yeah, perform well. So the quality of data should be better. Okay, for example, suppose you got data. Okay, you got data of the customers, and 5% of the customers, 5 or 6% of the customers have not have not filled have not filled oh have not filled, okay, their age, or have not specified their age. In the situation, what you'll do? Okay, whether you will put them as an outlier, you will drop them, you will not use them, or you will fill the missing values. Okay, fill the missing values, because data matters. The data matters because data is not very cheap. But even if you have sufficient data, and if you're not having the quality of data, how you will make the decision? Okay, how you will have this in your mind, that I have to use the data for do what? And for that, we should spend more time in cleaning the data or extracting the real thing from the data. Okay, the real thing, and we need to spend time to clean the data. Okay, to fix them or discard them, and making decisions. Okay, the team there. So that is why it is a very good practice, and that is why the data science is there, because they clean the data, they make traces in data, they track about the data. Okay, that is the thing. Because even if you have sufficient data and no any quality of data, you're never going to have the prediction, you can never have the patterns in it, and you can never make good performance well. Okay, moving ahead, irrelevant features, a very good thing. Okay, even if the data is good and you have irrelevant features, you're never going to make it, because it is considered as success. Okay, it is considered as success to come up with the data, okay, which contains enough relevant features. Okay, in machine learning, it is considered as success if you come with the data with relevant features. With relevant features. Okay, because if you have sufficient data, you have sufficient data, you have representative of the data, all representatives of the data, you have good quality of data, you have good quality of data, but still you have the features which not making the sense. Okay, now we have to train our model. Okay, we have to train our model on the good sets of features, and if we don't have good set of features, it is totally waste. It is totally waste. That's why there is feature engineering. That is, there is something called as engineering feature engineering, in which what we do is that we make the features of the data relevant or useful by some techniques like feature selection, the feature that we want to use which makes sense and which will perform, which will have last longer, measure on the performance, which is useful. Okay, what I'm trying to say, I'm fumbling or whatevering, but it is. Okay, so feature selection. Now number two after feature selection, there is another technique called feature extraction, in which we extract or we only choose those features, or we combine the existing feature to have uh, to have a more useful one. Okay, to have more useful, we select features which is useful. Okay, now we combine features to one useful, to have one useful feature. Okay, and creating new features depending on the situations. Okay, and creating new features for having a better performance. Okay, so there was it is having relevant features. So that is all about the data side, that if our data is good, our model will be good. Now talking about algorithm. Now talking about algorithm talking about algorithms. So the number one thing that can go wrong in algorithm is that it can overfit the data. Okay, it can go overfitting. So overfitting, which means overgeneralizing. I have talked a lot of time, and even if you would be knowing about overfitting, if you don't, you can go and check out the lectures that I put on the on my channel. Okay, so the overfitting or overgeneralizing. My God, my writing is getting like a doctor. I need to see to a doctor. So, uh, overfitting, in which the models overgeneralize and it performs well on training set, but it performs poorly on testing set. And that's what overgeneralizing is. So now to prevent from overfitting, we constrain our model, we constrain our model. Okay, to make it simpler. Okay, to make it simpler and reduce the risk of overfitting, called regularization. regularization So there is a new term called regularization. So regularization is it's simple, which means that it used to prevent the model to get overfit. Simple as that. Now, how regularization used? So regularization use simple hyperparameters. Okay, it uses hyperparameters within the model to prevent it from overfitting. Okay, it stops the model to get to the place where it shouldn't be. Okay, got it. So we use regularization to make it prone to overfitting. Okay, now moving next, what we have here, underfitting the training. data. So this is just opposite. Okay, overfitting and underfitting, just opposite words, but still it is a matter. Okay, so underfitting simply means that it doesn't even perform well on the training set, and it doesn't even perform well on the test set. Okay, and that's where we need to do, we need to do some, we need to come to some solution, or we need to do some, what you can say is, we come to some solution, or we come to the conclusion then how we are going to fix it. Okay, how we're going to fix the underfitting of the data. Okay, underfitting. So we need some ways to fix it. So the first way, so the first way to fix it is selecting a powerful model which has more parameters, so we can have more constraints. We have more constraints, or we can make it regularized. Okay, and feeding it, feeding it good features or useful features. Okay, to the algorithm using feature engineering, okay, and we should reduce reduce constraints on the model. Constraints, okay, constraints on the model, or we can say reducing the regularization parameter. So yeah, this is it. These are the main challenges in the machine learning. If you are building a project, it is very necessary. Okay, it is very necessary to look to these problems or challenges, because that can totally disrupt or destroy your project, or that will affect the performance in it. Okay, yeah.